question at Professor Nazarov from that starting with gathering to teach us all about the basics of quantum transport.
Thank you. I'm Nazarov. Nice to meet you. What I will do for you, I will give four lectures about really basic facts of quantum transport, which is a new field for me, because it did not exist when I was in your age. And other people kind of made it, and it was pretty much fair to go from very complex concepts and make it step by step very basic. Make it so simple as for students to swallow it without any resistance. Right. So I don't expect resistance from master students, but let me just expect it from you. So I will again go at simple level, master level. You can follow without much of, you don't have to make complex calculations in your mind. But it would be good if you just look at it a little bit critically and confirm this criticality by asking questions. I would really appreciate the question, but anyway, please. Right, so quantum transport. There's a book of quantum transport which was written with me, with Yaroslav. Here's the book, it's still available. It has many chapters. I basically concentrate on most fascinating aspects of quantum transport, which can be formulated as a slogan: any transport is scattering. So I will be talking about scattering of electron waves. First lecture, general motivation, general outline, scattered quantum waves. And I really will go very simple about quantum waves. Please don't get irritated, rather try to be critical. There are many funny questions I can ask about this. Right. Then what is most important feature of quantum waves, or any waves, is interference. So second lecture will be about quantum interference. It is, I would say, blessing that scattering for normal electrons can be extended very simply to superconducting systems and systems where spin is important, so-called spintronic systems. So third lecture will be about these kinds of scattering, typical for superconductors and spin-dependent devices. Right? And I will finish this short course with making bridges. First bridge, simple bridge, will be between quantum description of transport and Ohm's law, which you probably learned at school, and it doesn't seem to fit at the side, so I will spend quite some time to do this. That looks boring. What is less boring, that in fact one can describe complex phenomena of scattering of quantum waves in a way which is similar to Ohm's law, which is similar to Kirchhoff rules. You don't have to address individual wave patterns, but rather use conservation laws to arrive at, say, quantum circuit theory, quantum Ohm's law. That's the program for coming days. 4 lectures. So number 3 and number 4 I will give in a row. It will be also Friday evening, so it's extra challenge for all of us. But okay, I hope you won't be too much bored. Right. Let me try to play a simple game, which is rather silly, but perhaps very instructive. The game is to compress the essence of something very big in just a single sentence. Let's talk about all natural sciences. Let's talk about sociology, economy, mathematics, just about natural sciences. What would be the price? I asked many people, and of course you never get a consensus, but many people actually agreed that this price would be that everything consists of atoms. Having that in mind, one could understand physics, chemistry, biology. One could think of atoms as the fundamental building bricks of anything. There was and still is ideology called nanoscience, which had a slogan, "Let us shape the world atom by atom." And it looks rather fascinating. You just give a program, and you can make nanostructures of anything, any combinations. You really can build the world atom by atom. That would be possible perhaps in 300, 400 years, I don't know. But the atoms is quite an old concept, which is due to ancient Greek philosophers. Experimental observation delayed a bit, yeah, till the mid of 19th century. So what is the new idea? What quantum transfer tells us? And to do the same as quantum transport, that's short. It is not important that everything consists of atoms. There are some other laws, some other concepts which are specific to this field, of course. One would not apply these concepts in biology, but still it's very different. It's not important that quantum structure, nanostructure, really consists of atoms. Right, what is important, what is central object of quantum transfer? Let me just draw it accurately. This is the cube. In many talks you have already heard in this lecture, people talk about dimensionless conductance. This GQ is a conductance unit. Let's see if I remember correct formula. I think it is. The natural scale of the conductance. Surprisingly enough, it has very good simple explanation in terms of scattering, but it appears eventually everywhere. You want to characterize how strong interaction is in a quantum system. You go to the same scale. So I guess I can count, but I guess give it a course. I mentioned this GQ at least 20 times for 20 different physical phenomena. So that's central object of quantum transfer. All right, let's start. These electrons as scattering waves. I don't think I really want to go through this outline. No, just it has to prepare for what will happen. No. That part this would be really about your first quantum mechanical book about gravity. This will repeat it shortly. Then something which is not in the book is a description of nanostructures in a very paradoxical way. I will give you a statement to believe, and I will try to motivate this statement to tell how people eventually came to this concept. Right, then the rather technical part about scattering matrix. The slogan of this lecture will be resistance is scattering, conductance is scattering, quantum transport is scattering. So we come to Nazarov. Discussing restrictions and limitations. And then I will spend some time describing statistics of normal electron transfer. That was discovery, theoretical discovery made by mostly Dimitri Vitov. And observation was that scattering theory is good not only to describe single wave conductance of current. Scattering approach is pretty mighty to describe very fine details of electron dynamics in nanostructures. In particular, in the course of electron counting statistics, there will be some formulas and answers to these. Good, that's outline. We see it's very various, but I hope we will keep to that. Fine. Electrons as plane waves. Let's forget about any solid state physics you're exposed to. Let's take a very simple picture of electrons. There's a box. I put some electrons to this empty box. Where would they go? They go to eigenstates of the Hamiltonian, whatever they will acquire. They will go to wave functions which have certain wave vectors, momentum, right? So that is this wave function probability is such that each electron is uniformly spread over the box. Right, the wave vector is related to momentum, is related to energy for non-relativistic electrons. That is what you do not see in this figure is what I wanted to sketch here are wave fronts. So the space, three-dimensional space, electron propagates there, and it is a particle, but at the same time, it's a wave. So it's presented by this sequence of wave fronts. I don't think it's a big picture for you. Let's go to another stuff. Let us recall that one electron is not enough to discover a metal. We have to put many electrons into this metal. Electrons are fermions. So given these states, we can occupy them. We can occupy them. We can put either 0 or 1 electron to this state. Right, so let us try to count these electrons. And first step is to go to the space of weight vector and count how many states are there in small cube with dimension dkx, dky, dkz. That's how many states is there. To check your intention, what is this factor? What does it come about?
Okay.
Yes, it's 2 with index S, which, just not to forget that electrons have 2 directions of spin. That's why it counts the number of allowed states. Right, the next useful concept is the filling vector. So we just look at this cube, and within the cube we figure out what is the fraction of filled states. In that way we derive a function which depends on k, and this is filling vector. Having that, we could compute everything which we know, we want to know about the metal. Let's see, density, energy density, current density, all densities are given by integral over k, summation over the small cubes, filling factor comes in place, and then depending on quantity, there are different weight factors, either one or velocity times charge for current density or energy. So far, so simple. What my master students frequently forget about, that quantum mechanics by itself does not fix filling vector. So, from the point of view of pure quantum mechanics, any state is legal, is legible state. So, so filling vector is not fixed. It can be only fixed if understand that my metallic fluid, is a part of the whole universe and is kept in thermodynamic equilibrium with local thermal mass. Right. That finally fixes filling vector. It makes it a function of energy and chemical potential. Like this, tiny distribution. Right, here I plotted this filling vector in the fancy way. Horizontal axis is filling vector, vertical axis is energy, so you see it makes a step. The width of this step is defined by temperature in energy units, and this is chemical potential. Right, just to check how you good these numbers without computer, what would be typical ratio for room temperature between the width of this step and chemical potential?
Tens of thousands.
Thousands? So how do you count it? Please explain it.
Well, typical Fermi energy is electron volts, which
Yes,
translates to thousands of kelvins, hundreds, tens of thousands.
You took energy scale as electron volts, and you transfer 300 Ks to electron volts. That's how you count it. There are different realizations, of course. For instance, there are semiconductors, and there are Fermi energies that's like 30 millectron volts. Still, at dilution, at helium temperatures, Fermi energy is much smaller than the temperature smoothing of the Fermi vector. So that's why it's very simple and crucial concept for all transport. Transport occurs in a very narrow energy strip around Fermi surface. Why is it so? At higher energies we don't have any electrons to transport. Below, all states are occupied and no charge transfer can take place. Good. So we need to concentrate on energy strip close to Fermi surface. Right. Let us see. Let's get through yet another piece of elementary physics that's about waves. It's about wave guides. But if I look at it, it's almost magical ability for a human to change the constant, which looks pretty certain, to change the dimension of the space. If we would have only classical particles, it would be impossible to make it one-dimensional, zero-dimensional. But this is possible and even simple with quantum waves. Right? Let's recall how they do it practically. Suppose we have electromagnetic waves, that's three-dimensional, one wants to make it one-dimensional, so what one does, one makes a waveguide with impenetrable walls. Then possible wave functions are made of standing waves in y and z direction. The motion is discretized, is quantized in this direction, but it remains unrestricted in x direction. So we still have a plane wave, one-dimensional plane wave instead of three, and all other dimensions go to the fact that the modes are quantized. One could say instead of a single sort of a particle, one electron has so many sorts as many modes. Or they eventually use it such language when they talk about wave propagation. All right? Look at the figures here I just sketched. Standing waves, figure 2. Figure 3, I again try to express the same with a particle which bounces between the walls and propagates on. Very good. Let's come back to the expression of the energy. Let us figure out how energy is manifested in this context. So there's kinetic energy of propagation in x direction and kinetic energy for propagation in perpendicular directions actually became a potential energy. There is some energy which doesn't seem to be kinetic. Good. Waveguide. If someone is confused about this, please, again, it might seem simple, but an interesting question would be very simple. Okay. Yes?
What do you mean by standing wave? What do you mean by standing wave?
Okay, a standard wave comes from the fact that the wave field should be zero at two ends of waveguide. Let's look at one dimension. That's why the wave can be either this one or this one, or vice versa. That gives rise to quantization. Each wave can be characterized by a number of nodes in this wave. So there are discrete standing waves. More questions? Yes?
For example, we can describe not only by standing waves, yes, but if we take some material and want to measure transport from, for example, let's say it will be a square material, and we put contact here. So transport will be like 1D, yes or no?
Just a convenient model where I can separate direction in X, Y, Z.
Yeah.
Just to kind of get a notion that this is possible. Then one would just, whatever, it's not forbidden to talk about topology in this audience, let's make topological argument. If I change it a little bit, if I would not make it ideally squared, or, for instance, I could introduce more realistic boundary conditions, where it's not absolutely zero, but something. It will change concrete expressions for energies, we have some quantizations, but the factor remains the same. There will be quantized modes, which are one-dimensional, which will propagate in a certain direction. So that simple model just shows the scenario, and one can prove by topological argument, by continuity, that the same situation will be realized in general. Does it answer your question? Yes?
The direction of the propagation is defined by the standing wave, or that is defined by the propagation?
Standing waves are in perpendicular directions.
So you said that in a specific direction.
Yeah, that's precisely the point. This is what you make. It's not what nature gives you. You really make it in a certain fraction. All right, that was waveguide. Let me add, okay, you might still remember with you that this is from your first quantum mechanical book. Was it page 17 or 38? You might remember this. Which page? Which page was that in your book? Okay. Which page? Page 10. Wow, that was a great book. So it's yes, first quantum mechanical problem, which was kind of ticked over there. It's a one-dimensional problem that did not seem realistic by the time you read the book. But now with waveguides, we can treat it realistically. We know that one-dimensional electrons do exist. Right, so how do we solve it? We have potential which is constant in three regions, and in principle, there are two solutions in each region, corresponding to two waves at the same energy propagating in opposite directions. Let's concentrate on a certain solution there. On the right, our wave, our electron propagates only. Okay, now we have a problem because my left is not what is your left. Okay, electron goes there, only there. On the other side, you can see two waves. One of these two is inclined wave, another is reflected wave. All right, and something happens in this barrier. If it is constant potential given the barrier, we can quantify it, we can solve equations with two boundary conditions. What for boundary conditions? Continuity of wave function and derivative. There are two of them. 4 equations for 4 unknown variables. We solve for all these unknown variables. I could think of a more complex structure. I could put 100 variables. So I don't care about most unknowns I have found. What I care about transmission and reflection amplitudes. That's what I want to know at each energy. Right? I don't care. I want to disregard all details in the nanostructure. There are people who don't like it. For instance, there was a book which is called Quantum Transfer, and that was completely about representing potential scatter atom by atom. There are also numeric packages which can do it for you, but I don't think it's important. Again, for a transport, what we know, what is important is a chance to go from the left to the right, is a chance, and this chance is given by squares of reflection and transmission amplitudes. Fine, let's see, let's talk about transmission probability, all right, that we know, it's transmission coefficient squared, reflection coefficient squared is reflection probability, they have to sum up to 1. That's all on page 10 of your book. I hope, right, what I want you to show. Transmission versus energy. For completely classical barrier, I would have absolute reflection till certain energy. Okay, that's barrier height. So it would go something like that. Let us see. There is thin barrier and thick barrier. Which is more quantum? That's a personal question, but let's answer this question.
In one.
Thin, right. That's because I implicitly compared the barrier thickness with the only parameter which can appear with the problem, namely this electron wave at this energy. And this is quantum. Fine. What we see, thin barrier, thick barrier, they have different transmissions below the barrier. It's called tunneling, or non-quantum mechanical tunneling. Classically forbidden process still can happen in quantum mechanics. Right. Yes. And on the left, it looks very harmonic. If you look at on the right, you see something strange for a thick barrier. It doesn't approach one monotonously, but makes some wiggles. Who can explain this?
Multiple reflections from inhomogeneity, so the potential at the two edges.
Yes, right, but just let's point out what are these inhomogeneities.
Steps.
Yes, sir. There are 2 steps in this potential. Each of the steps kind of reflects the electron, and interference of these 2 reflected waves provides this wiggly pattern as function of energy. Right. We care about transmission probability, transmission coefficient. Now I want to serve you something. I want to serve you some idea, and again, as I mentioned shortly in the beginning, it was revolutionary idea in quantum transport. Like in any revolution, till certain date nobody believed in this idea, and in like 5 years, nobody believed in opposite ideas. Right, sure, what was the starting point? We talk about realistic nanostructure, small objects with certain number of metallic leads attached to it, some small conductor. And it can be very complex. Here, sketch it, it can have some design, some defects. However, whatever the complexity with respect to electron transport, this nanostructure can be modeled with a waveguide, certain number of transport modes in this waveguide, and transmission coefficients of these modes. If you believe that the world consists of atoms, it's quite a logical jump. But still I insist on this point. Again, there are many confusing questions one can ask, but yeah, if you don't ask them, I would not concentrate on these. To solve your point, I will go through several steps, and hopefully at the end of the day we understand it better and will be ready to accept this. Right, let me start with adiabatic quantum transport. Let's take a waveguide of variable cross-section. Let's change the width of this waveguide. What we know that the energy of an electron in this waveguide will depend on its dimensions. So both A and B corresponding to Y and Z dimensions can depend on X. Then this energy, which is kinetic energy of perpendicular motion, becomes potential. It becomes potential because it will depend on X. It will depend on coordinate. That's why this right picture arises. Here, I guess it's still with the all. Electron sees the constriction as a potential barrier. What might be a bit confusing that the height of this potential barrier is not constant. According to this formula, it depends on the mode. It is different for different modes. Okay, let's recall that we are interested in energies close to Fermi energy, so let's concentrate on a certain energy in the setup. And then we see that for some modes, the potential barrier is lower, and these modes could propagate through the constriction. While many other modes, which are given by pink, this drawing, have to be reflected. Yeah. That's how I distinguish between open channels and closed channels. Each channel is a combination of NY and NZ. And you see that for a given energy, some channels are open, transparent, and some closed. All electrons coming in these channels are reflected back. Good. So, then I want to derive any historic. Yes.
The x is an arbitrary parameter.
What does that mean?
X.
X is a coordinate, so I'm talking about electrons go from the left to the right as plane waves.
And then
X is coordinate.
A and B. A and B.
A and B are from previous transparencies. It's the width and how I call this dimension, depth of the waveguide.
Yes. So it's like
X direction is the third perpendicular direction. Okay, let me get back. So this is constriction of the this A. If it doesn't depend on X, this is what I described previously. Now it does depend on X. Advanced question. Why do I call it adiabatic? What is the assumption which I made without explaining it?
It's like stationary adiabatic when you have this direction, so your energy is proportional to momentum, and momentum anti-proportional to that scale. So when you have
Well, I can formulate it so. Let me see. I want to make this variation very smooth, adiabatic, right? If I would make it a step, then, as we have heard, there will be some reflection from the step, right? So I don't want any reflection. So I make this constriction, the change of constriction width, the resulting potential to be very small. So no reflection, either transmission or full reflection. Right, so that is quantum contact. Let us count the current in this contact. Let us see. First of all, how can I do this? All right, this is constriction. I could take any cross-section and compute current. Since current is a conserved quantity, the result will be the same in any cross-section. Let's concentrate on one here. Right, what I see, first of all, closed channels. I see that all electrons which go from the left to the right are reflected in closed channels. Consequently, the current contributions in closed channels cancel each other. Very good. I have to concentrate on open channels. I do, and I look here, and I care about filling factors of the waves going from the left or going from the right. And understand that they just pick up filling factors of their origins, filling factors of their reservoirs. Right? That's why the transport persists only in narrow energy strip. Oh, let's see, it's something wrong with my figure. There has to be yellow filling factor, like this. Right. In this case, I'm sure that transport will occur only if there is a difference of filling factors between the left and the right. And indeed, transport can only happen if there is no equilibrium condition, and this shows the absence of equilibrium between the left and the right. Good. How about coefficient? Current comes with velocity, but for one-dimensional systems, density of states, if I go from integration over K to integration over energy, this is inversely proportional to velocity. That's why the coefficient in this formula is absent. Current is a sum over energy strips. For each energy, I have the difference of Fermi factors. The factor does not depend on velocity, doesn't depend on anything. Right, let us integrate our energy. Then what I get is just difference of chemical potentials, or in other way, the voltage implied. So, I see now that the current is proportional to voltage. Okay, it's good news. That's what we heard. Linear relation, Ohm's law. The coefficient of proportionality, which is conductance, is the number of these open channels times some universal quantity, conductance quantum. People didn't believe that because it was relation. Still, there's much effort goes to material research. It's active research rational. Of course, it's useful. But what does this formula show? It doesn't matter how do you make your nanostructure. You can make it from copper, from silver, from heavily doped chromium dioxide on sapphire substrate. You can make it from wood. It doesn't matter. What determines the conductance is the number of open channels. It was somehow very simple idea, which was difficult to accept.
Why 1U?
Yes? Why?
Because number of channels. No? Number of channels. Why that?
Yeah, okay, yes, sure. Why we've got? You understand about the waves? Why we've got? All right. The best way to understand it is to look at it experimentally. Right? So many years ago, and around that it has happened in Delft, people really decided to measure the conductance of the constriction. Okay, they took two-dimensional electron gas, which is in this figure is white. They put the gas on the top of it and applied voltage to deplete the electrons from gray regions. Thereby, they have made a constriction in this gas. Changing the gate voltage, they were able to change the width of the constriction. And this is what they found, almost ideal quantization in terms of, in correct units, in units of conductance quantum. That was a, I would say, turning point in the history of modern quantum transport. All right. And your analysis of this paper didn't quite understand why it is one-dimensional. Because the constriction that they made didn't look like a waveguide, it wasn't really prolongated. Nevertheless, it worked. What is important that there are some modes come to this constriction. Perhaps it's better to see the next transparency. Okay, let's start with adiabatic quantum transport. And let's increase the number of incoming channels. To do so, we just increase the width. We put it to infinity, so there are infinitely many modes coming. But we can count these modes. And we can recognize the fact that only few of them actually can go through this constriction, or replace this constriction by arbitrary non-structures. Right. Of course, the quantization which I've shown is not ideal if it doesn't have to be. Because any reflection from this potential barrier, if adiabaticity is violated, then it doesn't have to be ideal. One could take into account extra step domain. And with this, one can describe this experiment. So that's basically completes the circle of my proof, which included first pages of your quantum book, experimental curves, and some hand waving. Did my message go through? Do you have doubts? If you have, let's talk about this. Yes?
And how did we get to the current that goes through the formula of the functions? How did we get there?
Is there some reflection? I talk about the situation when there is no reflection in open channels. I'm going to generalize it. It's very simple, just the next page. Okay. This is called Landauer conductor. Other native German speakers in this office. What is Landauer? I'm Landauer. Nine. It's a carriage used in the 19th century. A carriage, you could just put horses in, and this is Landauer. But it was a person with this fancy name. The person was rather unstandardized at that time. He doesn't want to work at universities. He worked at IBM Research in New Jersey. And that's why when he put, let's see, I guess he got something like, okay, Landauer formula. When he put this simple formula, nobody believed him. You're from universities, what can you say about quantum scattering? Get it right, but it took quite some time for people to understand that he was right. Let us see, let me get a little bit back and let me just try to introduce scattering metrics, and under them let's arrive at our formula. Let's see how I'm doing with respect to time. Actually, bring it back. I need to accelerate. But one could also get the result of the lectures. I could pick up tell something from this lecture next time. But let's try to get a bit faster. Anyway, I will be talking about rather moment things, but fundamentals. So please be with me. We have a system of electron-based. Let me for this lecture take two terminals. Electrons can come from the left or from the right. There are different number of channels which can come from the left and from the right. And I want to figure out what are the relations between incoming and outgoing waves. And this relation is given by scattering matrix. Yeah. For matrix, one needs two vectors. So one vector is a vector of amplitudes of all incoming waves. And B in this formula is all set of outgoing amplitudes. All right? So that's why I derive a matrix. So if I send a certain incoming wave, it will go to all different outgoing waves, given a row of this matrix. Then I check another incoming wave, I get another row. So in that way, I build the whole matrix. Fine. Still, since we are talking about Yuli's thermal structure, it is convenient to separate this matrix. It can be of any dimension, but I would like to separate it into 4 blocks. Those are waves which come, let's see, from the right and go to the left. Those are waves, come from the left and go to the left, reflected. Those are waves reflected from another end of the structure. And those are T, transmitted waves, either from the left or from the right. Block structure of scattering matrix. Let's see what are general properties, is imposed in the scattering matrix. Most important condition is a condition of unitarity, which just describes in a two consistent quantum-mechanical language, very simple thing. All incoming particles are reflected. All outgoing particles came earlier to the structure. No particles originate in the structure. Conservation of current, conservation of all amplitudes, that leads to unitarity of scattering matrix. Do it in blocks, write unitarity in one block. That's what we can. We can immediately see its correspondence to chances. Reflection probability plus transmission probability is 1. Right. Another important property is time reversibility of the matrix. So transmission from the left to the right is the same as transmission from the right to the left. Who of you ever seen a video recorder? Right?
As in,
Your brain used this at home, and there's a possibility to change the direction of the movie, which is unfortunately absent in modern computers. Okay, someone can make a movie about the electron going from the left to the right, and on this old-fashioned analogous device, just rewind this movie in opposite direction. You see that the same electron propagates from the right to the left. So if there is a possibility of time inversion, these amplitudes have to be the same. The stories of this electron must be the same. Right. Simplest example, and indeed quantum transport is best understood with very simple examples. One channel scatters. 2 incoming waves, 2 outgoing waves, 2 by 2 matrix. Is there a question?
Yes.
Yes, please.
Is time reversibility some additional assumption that we make or something?
Yes, for instance, it depends on how strong is magnetic field applied to your sample. With magnetic field, one can, we will discuss it in some details later. With magnetic field, one basically breaks time reversibility. Yes?
In all of this story, you imply that there's no inelastic scattering happening in the structure.
Yeah.
And yeah, is it a common situation in all those nanostructures?
Look, I'm still at the level of first quantum mechanical work.
Okay.
I don't there was an elastic scatter in that work. It will come a bit later. I will describe, in most cases, I'm an honest person, so at some stage I will give you a list of restrictions and limitations on this stuff. Right, so this matrix is characterized with transmission coefficients. This is natural, but if one counts possible parameters of unitary matrix to better unitary matrix, one also finds two extra phases. Let's keep it in mind that the scatterer has parameter, which is transmission, but also the parameters which are hidden. Two phases.
Excuse me, I'm a bit confused. Shouldn't there be a transposition? I mean, you have T equals T prime. Isn't there T prime transpose? No, there where you have time reversibility.
Yeah, at the moment I also assume time reversibility. So there are two independent phases. If I didn't, I believe there would be three independent phases.
No, above where you have time reversibility, you have a statement that T equals T prime.
Mm-hmm.
Isn't T equals T prime transposed from?
And they should have the same form factor. If you have
Yeah, it's again about looking at
this,
this
get a
movie.
transposition would spoil it.
Good. Let us see. We came to Landauer formula. So what Landauer says, one can use the same formula as we derived for open channels with a minor modification. One has to insert to this formula a transmission chance. So still the same formula, conductance, conjunct in front of it, summation over all energies. It would be much more efficient to discuss these things with me. I think absolutely yes. No problem. Good. Transmission cases. And again, one can look at low voltages, for instance. One can rewrite this formula if transmissions do not depend on energy. This is the Landauer formula. For any nanostructure, conductance is just the sum of transmission coefficients in all channels times conductance quantum. Right. Good. Again, people didn't believe because academic research should not be that simple. The same was with Gustav Kirchhoff, which was the person responsible for all electric machines we ever used. He made circuit theory, which made electricity available for engineers. Yeah. But it took him, I guess, 30 years to get professorship. Please make conclusions. All right, very simple-minded derivation of Landauer formula. Let's count how many how many electrons per unit time come to the constriction. Okay, the derivation goes along the same lines as I explained. This is that many. It's proportional to the width of energy strip, it's proportional to time, and there are just coefficients. That's how many electrons come to the junction. Then some of them pass with this chance. That gives us the current, that gives us Landauer formula. All right? So we just count how many channels come with that constriction in each, how many electrons come, to the constriction in each channel and sum up all these constitutions. All right. So now I can talk about restrictions and limitations. To be honest with you, I have to talk a bit. Indeed, as some of you have noticed, we have been talking about electron elastic scattering. So electrons pass in a structure without any energy loss. That more or less implies that they don't interact between each other or with other electrons in the room. So that's another assumption which has not been made so far, that electrons do not interact. So, how to go about these assumptions, whether one can fulfill them or not? It comes to my mind that nature is generally merciful to us. Or one could make it anthropomorphic principle. One could easily imagine a universe when there's no place for human life, that we exist. The same is limitations of our formula. It would work much more frequently than you would expect it. Right? What helps? One has to spell it out. Electrons do not interact closer to Fermi level. Let's make a democratic vote. Who agrees with the statement? Good. This statement is incorrect. Can you tell me what a small half of the word which I missed in this sentence?
Well, the scattering rate goes to zero as it goes.
Scattering rate of what?
Of electrons, just particles.
Yeah. Yes. It's not electrons which don't interact. Electrons, they do as usual, as it is in the books, they interact according to Coulomb law. The point is that excitations, charge excitations in metals are not electrons. They are quasi-electrons closer to Fermi. And these quasi-particles transport charge, and they don't interact with each other. The closer to Fermi energies are, the lesser is the interaction. So formally, I should have your pictures in solid state in all other courses. Anytime you talk about electron in condensed matter, you should have said quasi-electron. But in that case, there would be so many quasi, nobody uses it. Right? So we just deal with quasi-electrons, excitations in metals close to the Fermi level, without making that explicit. Low temperature voltages are good. Why? Because in this case, we are really close to Fermi level. Yes, your question?
Sorry, can you elaborate a little bit about why electrons do not interact close to Fermi level? Okay, they're quasi-electrons, but still why? I mean, I think about, for example, theory of hyperconductivity. I have a Coulomb force there, and I should take it into account, right?
Yeah, but they feel, for instance, Coulomb interaction, which is screened by other particles. That's almost obvious, right? Then how this screen works? So if the ideology behind is that closer to Fermi surface, you had less phase space for different excitations. That's why it goes to zero. Good. Low temperature voltages are good. Short structures are good. Why? Because while passing the structure, electrons don't have time to lose their energy to interact with other electrons. One could say, oh, after that it will have very complex history. But it has already passed, it has already contributed to the current. That's why we can disregard this possible history of its relaxation. Right. So in general, it's a bit obscure phrase. Limitations depend on quantity of interest, whether you measure conductance or something else. It also depends on the structure. Kind of a theorem tells us that any nanostructure will be described by a scattering approach in the limit of low temperatures and voltages. This theorem doesn't tell you at which temperature that it happens. This temperature can be 100 K, or it can be, as it is typical for contributions of magnetic impurities, it can be 10 to the minus 4 K. But anyway, for any nanostructure, there is some energy closest to Fermi surface where everything works as scatter. Good description and limitations. Oh, I have 20 minutes, correct me if I'm wrong, to talk about counting statistics. Yeah, I would take some water. So, counting electrons. Let's count electrons, but first we need to understand how to count correctly. So let's have a protocol for our counting. That protocol will work for any discrete events. One can just go to a hospital in night shift and count how many babies are born in this particular hospital. One can sit beside the window, look at the watch, and count number of birds which you have seen passing the window. Or one can count electrons, and perhaps you did this experiment in your first days, first weeks at university, when you learn about errors in measurement. Who of you counted cosmic particles in your first practical? Yes, it's about 20%. Okay, the experiment was very simple. You were given a guided counter. You just look at your watch and count how many particles you get. Then you make a distribution like this. How many counts do you have? You make a histogram of your measurement. After that, you're supposed to get average result and compute the measurement error. I don't know about you. It was my first day at university and I was extremely disappointed. By that time, I got a quite romantic impression of the physics. And I just imagined all these cosmic particles coming from distant galaxies. Perhaps there will be signals from some intergalactic beauties. And all that I put in a boring histogram, and all that I restrict to a single number. Disregard a wealth of information. All right, that's how physics works. One has to accept it. Counting is about taking this histogram a little bit more seriously. So let's talk about characteristic function of this distribution. Who of you can read the yellow letter? I'm sorry, it doesn't work for any projector. So anytime you see a yellow spot, it means letter I. Characteristic function, it comes from general series probability. One can use Fourier transform of probability. So I have probabilities of n events, I do Fourier transform, I get a function of some parameter k. K is just a parameter in Fourier transform. But why this is possible, why this is useful? For independent events, characteristic functions do factorize. It also means that our time interval is sufficiently wide, log of characteristic function is proportional to time interval. One who got it from the first try? We count events on a large time interval. There is some correlation time between these events. So, all events can be separated into boxes of correlated events. We know that lambda factorizes. That's why it is a sum over these intervals.
For lambda, it's rather a product.
Sorry. Log lambda is contributed by all these intervals independently. That's the same way as to say that this lambda characteristic function factorizes. So there is time property for any counting process with finite correlation time. Good. Why do we need it for? With this we can make elementary event analysis. If one really takes care of computing distribution from intergalactic beauties, making Fourier transform, trying to interpret it. Okay, let's not talk about cosmic rays, let's talk about counting birds. Suppose one knows this function, and then it will zoom in certain zoological facts. Some birds are single and don't correlate with any other birds. And there's a probability coming from this analysis. Some birds come in couples, correlate. That's probability to be in couples. Sometimes birds are gathered into flocks. Okay, there's a probability of certain flock size. So looking at it, one can learn quite a bit about the birds, but we are not about birds, we are about electrons. Even without knowing anything, we can understand this characteristic function in two limits. First of all, tunneling limit. And in this case, transport will be due to very rare events. Remember, the chance to jump will be very small. Events are separated by big times, events are independent. So this is the function, characteristic function for independent events. This is called Poissonian distribution. All right. That's the limit of very low transparencies. There is a limit of large transparencies. And what one can say in this limit? Electrons are waves. So each electron in the certain momentum state. This defines the current, and this state does not fluctuate. It is in a certain state. So counterintuitively, if transparency is absolute, one doesn't expect any fluctuations of the current. So it looks like electrons form a cube and march in very orderly fashion from one end or from one lead to another lead. They are in the state of plane wave. Good. Now let me show exact answer. The formula for the work of characteristic function. All right. I will use the fact that independent events contribute additively to this law. Let us see. Two electron spins, summation over two states, over two directions, that's trivial. All energy strips contribute independently to these statistics. Summation over channels means that electron transfers are not correlated in each channel. A healthy person would also add very trivial thing. Electrons coming from the left and electrons coming from the right should be anticorrelated. Okay? That's not what we see in the Witter formula. In fact, electrons going from the left and to the right are dependent. One can see from the formula level in this chart. That gives us probability of transmission from the from the left to the right. And that has some convenient structure. Number of electrons on the right times number of holes, lack of electrons on the right. So in fact, these processes of transmissions are accompanied by blocking factors on this side of this form. I'm an electron, I'm going to from the left, I want to get to the right, there has to be an empty place for me on the right. So electrons are fermions, and that many students actually don't understand this, at least in my class. That already means that they are correlated. Because there are no electrons as individual particles, electrons are fermions, are quanta of electron field. And the same field is on the left and on the right. Okay? Statistics contradicts to mechanics. Good. That was the bit of formula. Let me just give a simple example of those for electrons which are transferred in this direction. So temperature is vanished, whatever voltage applied is bigger than temperature. So we concentrate on this case. And I would say bluntly, the derivation which the Witter and Boses have provided was really a gemstone of theoretical physics of that time. It wasn't complex, but it was novel, revolutionary. Few people estimated it by that time, but that became clear in coming years. And we have the authors didn't like the fact that the answer one can explain to any street hooligan. Let me do this. All right, so there are electrons. We're all coming in a cube, and they use this scatter as a gambling machine. So they come in a cube, and with a chance of T0, they pass, and they're happy. And with chance 1 minus T0, they got back and they're happy. They lose in this game. Right, so to any person who understands the concept of gambling, this statistic is very clear. Right. I believe if this type of distribution was first described by Pascal, and he didn't gamble much by himself. He concentrated on scientific structures, but he got plenty of aristocrat friends who asked them practical questions about gambling. That's how Dutch formulas came about. Right. So that's a simple answer. Behind the best, the message which people did not appreciate before this explicit answer, that the electrons really don't come to the junction as independent particles. Rather, they form pretty ordered cube. Good. That was all about electron statistics. Let us see. I guess I can manage to give the main message in few remaining minutes. If you come to ATM machine to get some money, usually, I don't know what will happen with development of artificial intelligence technologies. Usually ATM machine doesn't care about nationality, about your eye color, about your credit history. It just cares about your PIN code and if you see money. So just a sequence of lines. One can put PIN code like this. Strange enough, the same is quantum transfer. A given nanostructure has very many complex details. But what quantum transfer cares about this nanostructure is a set of transmission eigenvalues. Let's talk about conductances of high conductance as compared with conductance of quantum. From what I said, it has to be obvious that these conductors should have many channels. Each channel, I plotted in this figure just with lines. These three sets of lines give me distribution of transmission, give me transmission realizations of transmission eigenvalues in three formally identical diffusive contacts with a resistance of 50 ohm. There are many details, many impurities, many uncontrollable things in these diffusive conductors. That's why transmission distributions are individual for each realization. If one talks about a class of diffusive conductors, like people of certain nationality of eye color, one uses the concept of transmission distribution. So in fact, if one takes sufficiently many of these conductors and makes transmission distribution of all this, one comes with a smooth function showing how many channels with a given transmission are there in certain transmission interval. Right, so we will. Oh, okay, let me just flash the last transparency. Those are transmission distributions for non-ideal tunnel junction. So in this case, we see that many channels have very low transmission, but there are also some which have high transmission. This is transmission distribution for a realistic quantum point contact where not all the transmissions are ideal, they're distributed somehow. Again, in quantum transport paradigm, each structure is individuality. And the design class, the class of nanostructures, is given by the shape of transmission distribution. Good. I guess that's it for today. Any remaining questions? Reaction, feedback? First lecture. Yes?
But this shape of the transition distribution, you have to find out. So is this approach? So when is this approach actually offering more?
We need something to characterize a class of nanostructures. We cannot shape the world atom by atom. At present day of technology, we cannot make precisely identical nanostructures. Suppose I have a fabrication technology. I make tunnel junction of certain resistance, certain procedure, and diffusive conductor about it. That's how I make nanostructure. I make it many times. And suppose I can measure transmissions in each nanostructure. Then I can make transmission. More questions? All right. Why don't you give me a little applause?